Hi, and welcome to week 4 of the survey. This is SOC224, and my name's Nicholas Harrigan, or Nick, and I'm your lecturer again. This week is big. Actually, everything in the first 6 weeks of this class is extensive, big, and there's a lot of concepts to learn. So if you're feeling overwhelmed, that is completely fine and normal. And that's because basically, I need to give you all the information that you need to be able to do your research proposals before you do those research proposals. And that means that this course has a lot of front loading to get you up to speed. Unfortunately, and I know this, you're not going to understand and remember everything that I teach you now. But what you will find is as you design your projects and then conduct your projects, all of a sudden a lot of the stuff that I'm talking about now will become incredibly relevant and incredibly useful. So at some level, you just need to ride with it a little bit and, let it fall over you. So this is it's all an introduction to concepts that will become incredibly relevant as the weeks go by, and particularly when you do your project. And that's also something that sort of lies behind the philosophy of this whole class, which is that by all the studies of education show that the only way anyone really learns, which actually we all know in real life, right, is by actually through hard work and practice. Realistic practice is what it does it. And the example I always love to use is like when anyone buys a new piece of technology, what's the first thing they do? Do they read the manual? No. What you do is you rip it open, you throw the manual to the side, you rip off all the plastic, you plug it in, you turn it on, you try to make it work. And when do you read the manual? When you start to run into problems. And that's essentially how I see these lectures in lots of ways. I know that you're not going to listen to them and read them and follow them really in detail. And I know that most education that you do as a student sucks for those kind of reasons. Everyone's like, sits you down and says, let me read you the operating manual for whatever it is you're learning, whether it's figures, physics, chemistry, maths, or, health sciences or sociological theory. When really what you should be doing, I think the way that people really learn is by sticking their fingers in it, ripping open the plastic, starting to play with it, and then they start to realize the questions they want to answer and they look at the manual. So, but at some level I can't just do that because then you'll feel completely abused and like I haven't taught you anything. So these lectures and all the other resources I'm giving you are really resources that I'm providing in advance. They're a bit overwhelming now, I know, but they will I promise you, most of this will become incredibly relevant as the semester goes on. One thing I want to point out with respect to this lecture is that I've done a whole lot of work on the front end as well in terms of putting together some materials that should help you, especially those who don't really like lectures. What I've put together for you, if you go to iLearn, this is how you see iLearn, scroll down to week 4, and then this will change a little bit as I update it, but there's a thing called under readings called concept sheet. If you click on that, and then open. It'll come down the bottom here, and then, but I've already got it open. You will see this thing. And this is the concept sheet for week 4. It's intense because basically we're doing the equivalent of about 3 weeks work in one. We're going through sampling, measurement, and surveys. But what I've done is for each of these key terms, I've given a definition and an example, and it's a little bit more detailed, a little bit more systematic than my lecture is going to be. Probably a little bit more boring as well, but if you need to revise any of these concepts, you can go through this concept sheet. You could read it before or after the lecture, or you could pause it if you don't understand something and read these. Okay, so just remember that's there. It's I think it should be very, very useful. So back to... Okay, so this week, we're doing something that seems boring, but ultimately is incredibly useful. We're learning basically about the starting point for what we call quantitative analysis, right? So using numbers. And we're using the survey, which is one of 2 main methods of quantitative analysis, I guess, the most common. The 2 are the survey and what we'll do in 2 weeks called the experiment. What we're doing here is looking at the fundamentals of building blocks for understanding how and why we do this quantitative analysis. What we do is we basically start in part 1 by looking at the concept of sampling. That is the notion that there's basically the idea that most quantitative social science isn't based on surveying everybody. In fact, almost no social science is based on looking at the entire world, right? We have to look at a little part of it and then infer to the larger part, draw conclusions about what's going on. And the 25 million people in Australia, there are 7 billion people on the planet. There is 40,000 students at Macquarie. 99% of the time, when anyone is trying to understand any of those populations, even a class, we don't ask everybody, because we can't. Instead, we ask a few people and survey a few people or do experiments on a few people, and from that we can draw conclusions about what really we should do. And that helps us make better decisions. It helps us get real knowledge about the situation. It helps us, if we're a basic social scientist, learn real social laws. So in part one, we basically learn around the principles of doing that so that we can then correctly draw conclusions about the overall population. Fine. So in that, we deal with things like what is sampling, what's a population, what's the universe that we generalize to, what's a sample, what are the different types of sampling you can do, and how do you actually report that sample as a statistic or variation of that statistic and so forth. We'll get into that in a second. In part two, it's called measurement. And this is like at some level, the most boring, and at some level, the most fascinating thing. Because with measurement, what we do is essentially say, how do we measure the world? And it's like, I don't know, we use rulers, or we ask people, whatever. It's not that, it's sort of obvious, isn't it? But what we do is we look at measurement, we look at how there really are only a few fundamental different ways of measuring, or of measurements that you can have of things if you want to turn them into numbers. For example, you can have categorical variables, which are basically like, say we might pick out like, what major are you doing or what degree program you're doing. And none of them, they're just categories, right? But we have to give them numbers because computers need numbers to do analysis. So the categorical variables, there are binary variables, a yes, no, are you dead or alive, are you pregnant or not? And then there are continuous variables, which might be like weight or height, or it could be some social variable like your level of introversion or the number of friends you have. What we learn in this section on measurement is, and I think what's profound about it, is how to transform things that we thought were unmeasurable into measurable things. So, I mean, just to choose a cliched example, how many people have you heard say that love is not measurable or a relationship is unquantifiable? Well, I'm sure that's true because we can't capture everything in it, but many psychologists will want to agree, and many sociologists will want to agree. They will say, well, no, actually, we can have a series of questions we can ask people and work out how much they really do love each other. We might, what sort of qualities that relationship has. We could ask them how much time they spend together, how each of them feel about each other, what the level of commitment is, what things they have in common, etc., etc. And through these, they might be able to develop a scale for the amount of love in a relationship. And the crazy thing is that particularly sociologists and psychologists manage to invent a scale for just about everything, and make almost any concept you can think of quantifiable. In the last section, it's a very practical section. The last section is just the practical stuff about doing surveys. It's sort of a bit like some of the practical things about doing ethnography we did last week. So we learned how to design a good survey, what good questions look like, what bad questions look like, what do we call a survey? Is it really a survey? Well, actually, it's really a questionnaire. And what's the difference between a questionnaire and an interview schedule? And the thing about this is it's just actually super useful because you're going to have to design a survey by week 7, and you want it to be a good one. And then over the break and in weeks 8 and 9, you're going to be collecting that data, and you kind of don't want to screw that up. So the survey section is pretty straightforward. Anyway, that's the sort of overview of where we're going and also why it matters and why you should care about it. But let's get right into it now. So, part 1. So I've divided the lecture into 3 parts. Part 1 on sampling, part 2 on measurement, and as you saw, part 3 on the survey. So we're doing part 1 now. And this is, if we look at, when we talk about sampling, we're going to talk about 3 main topics in this lecture, or this part of the lecture. We're going to talk about the types of non-random sampling, and then foundational context for really random sampling and statistics. And then we're going to talk about types of random sampling, because there's not just one. Why this order and why these things? Basically, non-random sampling is important because actually there are multiple different ways that we can do research that is not random, but many of them are okay or good enough for the situation. And then once we've done those, we'll start moving on to, all the technical jargon under what I put under foundational concepts, and then we'll look at the sort of gold standards in terms of good random sampling. Okay, so types of non-random sampling. There really are 4 that most people talk about, but I'm sure there's more than this. They are convenience or haphazard, that's one type, quota, purposive, and snowball, as you can see. Now, let's move in and look at convenience. Convenience is basically or haphazard, is basically what many people will call random, lay people will call random. Like almost every single class I teach and every single set of presentations I watch, someone will say, we surveyed everyone on the street, anyone on the street who walked past, so that was random sampling. It's like, no, that is not random sampling. Random sampling has to be mathematically random. Everyone who is in your population needs to have an equal chance of being in the actual study, of being selected to be a participant. Convenience or haphazard sampling should really just be called sloppy, whatever you want to do, sampling. I've given the example of a street corner. If you stand on a street corner and survey people, and you're actually trying to, that's just haphazard or convenience, unless you happen to be targeting the population of people who go past that street corner. But again, it wouldn't be clear why. When you just collect things ad hoc, you just survey your Facebook friends to find out about low-wage workers, that's convenience sampling. Often it's the best you can do, and often it's enough. So many market research companies or other organizations will do this just because it's quick and cheap. Okay, moving on, the second type of sampling we're going to talk about is quota sampling. So quota sampling is basically where you do convenience sampling, but you actually also, as you collect those people that you've done the convenience sampling of, you put them into buckets. So let's say you know how many men and women there are in each degree program. At Macquarie, or here the example I've got is you've got the census for gender and citizen, non-citizen, so 2 variables. And so how many men there are, how many women there are, how many citizens there are, how many non-citizens there are, and also how many men citizens, women citizens, etc. And from that, you can work out the proportions. So say you're going to survey 300 people, and you know that in the population, 25% of them say 40% of them are male citizens, then you make sure that 40% of the people you survey on your street corner are male citizens. And once you've surveyed enough male citizens, you just stop. Right? Once you're doing a survey of 100 people, once you get to 40 male citizens, you stop collecting surveys from male citizens, and etc. And you fill up, and it's called quota because there's a quota of how many people with each characteristic you would survey. And it turns out that this is a remarkably powerful method for actually making your data valid, and much, much, much more accurate than a convenience sample. In the next type we're going to talk about is called purposive sampling, which we talked about last week under qualitative data collection. Basically, with purposive sampling, what we have is a situation where we basically are sampling based on our best judgment, with the idea of getting a diverse representation and variety in our sample. So I might have given the example last week that with one of my studies, we surveyed migrant workers in Singapore in the construction and marine industries. Marine means they build oil rigs or repair ships and so forth. And we didn't want to just go for convenience because we would have surveyed almost all Bangladeshis. So instead what we did was we also deliberately reached out to survey Chinese workers and also Indian workers. And this was purposive. I mean, we didn't know what the proportions are. They're a state secret of different workers, so we couldn't make it actually quota, but we just made sure we had variety in our sample. So it's purposive. The last type, which you probably haven't heard about, is called snowball sampling. This is a snowball because you use the people who respond to recruit the further respondents, and then the people who you recruit them to recruit further respondents. And so like a snowball, it picks up snow, it gets bigger, and then you complete the data collection by having enough respondents. You generally use snowball when it's very hard to find your population. So say you actually had students at my previous university who wanted to interview student sex workers, and they used snowball sampling. They knew someone who was a student sex worker at the university, and they interviewed her, and then they asked her to invite her friends, etc., etc. I've put here as an example weed smokers, so people who smoke pot or marijuana at Macquarie, and say you wanted to do a survey or a study of them, you would use snowball sampling probably because, I mean, actually, it's given how many people smoke marijuana, you might not need that. But maybe heroin use or something like that, a little bit rarer. But basically, you could recruit people from the respondents who've replied, and it works very well. Now, in really established research that has got funding and so forth, they actually tend to give out vouchers. So what they will do is they will give a voucher to, say, a heroin addict or such, or heroin user, I should say, and they will, and the voucher will say, if you come back, if your friend comes back, we'll give you $20 and we'll give him or her $20. And so there's a finder's fee that's paid, and that tends to work quite well. The type of populations that get studied by snowball sampling is a very unique type, but a really good one to understand. It's called a hidden population. These are generally groups who suffer from some sort of stigma or even potential legal sanction, and so try to not be socially noticed or seen. So it could be drug users, criminals, sex workers, or any stigmatized group. It could be some religious cult, it could be a terrorist group, etc. All these can be very useful for finding. All these are hidden populations that would be useful to study with snowball sampling. Okay, so that's the end of types of non-random sampling. We're now going on to foundational concepts. What we basically do here is we move from the notion of what's the difference between a census and a sample, and then on to the difference between a universe and a population and a target population and a sampling frame and a sampling element. These are all these here are different parts of the people you are sampling or surveying, and they seem not that different, but they end up having very different implications, and it's good to use these words correctly. We'll then move on to talking about two really key statistics we're interested in, the population parameter and a sample statistic, and then we'll talk about variability and confidence intervals. So basically, this is where we start to get on into the realm, close to the realm of talking about statistical significance and ranges within which we actually know something is happening. Let's move on. Let's go first. Okay, so census versus a sample. It's key to know that there are two different things you can do when you do a survey, right? Or any other similar sort of, but they're basically surveys or questionnaires. You can either do a census, where you survey everyone, or you do a sample, where you survey a small number of the population to try and represent everyone. So the word census these days is almost synonymous with the Australian federal government census in Australia or the government census in other countries. This is an exercise conducted every 5 to 10 years, depending on the country, where the government goes and tries to do a survey of every single person in the population. And through doing this gets an idea of what the population looks like and what their upcoming needs are going to be like. The word census in our case doesn't just mean the Australian government census. It's the name of a type of survey you do, and it is when you survey everyone in whatever population that is, so that you're interested in. So if I do a survey of all 108 people in this class, that is actually a census. It's not a sample because everyone has done it, or everyone been invited to do the survey. If I did a survey of everyone at Macquarie University, 40,000 people, that again would be a census. A sample is when you pick a small number to represent the many. It's sort of obvious, but you may, often to public opinion polls, they will, or to understand how people are going to vote, they will do a survey of 1,000 or 2,000 people. You generally don't need to do a survey bigger than 2,000 people. It turns out it doesn't add much value, no matter how big, whether it's the whole American population or the whole Australian population. So you do a survey of 1,000 or 2,000 people, and and through doing that, by getting the right 1,000 people, then you will actually be able to generalize to the whole population. So I guess that's something, and that word generalizing is crucially important throughout the time we're talking about surveys and statistics and so forth. You have to remember that most statistics you do in the social sciences and elsewhere is actually about drawing conclusions about the larger group. They're not about drawing conclusions just about the particular people you talk to. And the reason for that is because we're interested in bigger questions, even if the administration surveyed 1,000 Macquarie students, they're not interested in those 1,000 Macquarie students. They're interested in what that tells them about all 40,000 students at Macquarie and how they want their lessons run, or how they want the lectures organized, or what sort of subjects they're thinking about doing in the future, or why they might want to do a master's program or such. So they're not interested in those 1,000 per se. They're interested in what the 1,000 can tell them about the 40,000. Now, when we are and so that 40,000 in the Macquarie case is what is called the universe, which you can see here. The universe is the people we generalize to, the people who we draw a conclusion about from the small set of data that we have. Many people doing basic science or social science are generalizing to all of humanity, right? So they're saying this is true of humans. Humans do this. Humans are status-driven. Humans are sexist. Humans are whatever, right? When you're doing your study on low-wage workers, in many ways you'll probably be trying to generalize to all low-wage workers. Even if you can't, you'll try to, because that's the interesting question here. What are the problems Australia faces? What are the problems that low-wage workers face? There's a joke here, which I will tell you, which is that most psychology studies try to generalize to the rest of humanity. So you'll read all these studies, but actually there's a real issue there, because do you know who almost all psychology studies are based on? First-year psychology students. I've heard that they are the most studied population in human history, and I think it's probably true. They're mostly women as well, by the way. So the irony is that you have, and they're mostly in developed English-speaking countries. So we have all this psychology literature all out there, which is supposedly about what humans are like, when they're really about what 19-year-old first-year psychology, mostly female, mostly English-speaking, first-world students are like. And that's an interesting sort of disjunct between the actual surveyed or target, the population that is being selected from, and the universe to which the generalization goes to. Okay, so when we move from the universe, the next level down is actually the population. So the population in this case, the population is basically an expression of the people you want to study in general terms. What we're going to do as we move on, we're going to draw the difference between, shall move on, a population and what's called a target population. So if the universe is all the people you generalize to, the population is the people you're aiming to study, expressed in very general terms. So it might be Australian workers. I want to study Australia. I want to study Australians, or voting age Australians, or I want to study Macquarie students. We then draw a distinction between that and the target population, being the target population is those things expressed, the same group, but expressed, that we're targeting, or that we are planning to study, but expressed in very specific terms. So we might be studying Macquarie students, but we can, as a population, but as a target population, we're talking about all Macquarie students enrolled in April 2019. Or we might be talking about all Australians who are over 18 and are enrolled to vote. Or we might talk about all, what else are we talking about? We might talk about all people who are earning below the median wage in Australia in 2019. That's an example of a low-wage worker target population. However, that's still not actually who we do our random sampling on. It turns out that there is another concept that's crucially important, and this is which is called the sampling frame. So, if the target population is who you would like to study, express in very specific terms, the sampling frame is actually the people you get to study, because the sampling frame is the actual list you get. So, maybe I misspoke before. With the Australian population, you might say, or the Australians over 18 who are citizens, you might say, my target is all Australians over 18 who are citizens and enrolled to vote. That's the target population. The sampling frame would be the actual list of enrolled voters given to you by the Australian Electoral Commission. The sampling frame is a physical thing. In this electronic world, physical means different things. In the case of Macquarie Uni, if you could, it would be the list of all 40,000 students and their emails and their home addresses or such that is given to you by Macquarie University, which they probably wouldn't be able to do unless there was a very legitimate business reason for it. So the sampling frame is that list, right? And the key thing about that list is that with that actual list is actual people who are going to do your survey, and from that you can, again, actually do random sampling, right? You can actually, the main way you do it these days is you put them into an Excel spreadsheet, and then you put a random number beside every row, which is each person, and then you sort by the random number. Like there's a random number generator in Excel, which just equals rand, 2 brackets, open bracket, close bracket, and you put that in, it generates a random number next to each name. You sort by that random number, and then say you pick the top 1,000 people. Well, that'd be a random sample of 1,000 people from the 40,000 students at Macquarie. And I've actually done this at my previous university. Before, Singapore had really good, well, not really good, very strong data protection and data sharing laws. The university was quite happy to share with me the list of all students, for which we could do a really proper, nice random sample. It wasn't for very serious stuff. I don't know. You could argue whether it's ethical or unethical, but what's done is done, I guess. Anyway, so that sampling frame is, as I've said, the list of actual potential participants, the actual list of potential participants. Each of those potential participants is what we call a sampling element, right? So each person in that list of 40,000, each person on the federal electoral roll, they are all potential participants. They're all what we call a sampling element. It's just a definitional thing, but it's important to sometimes express these things very clearly. Okay, so now we move on to the stuff that starts to get tough. So we do a sample from that. We say randomly pick one person, 1,000 people from Macquarie University. Let's just stick with that, or 1,000 people from the Australian population. And there are two things, right? Generally, I mean, the easiest way to think about this is in terms of thinking about what we want to know, the simplest thing we generally want to know is the average, like the mean of that population or the median, some central tendency of it. So we might, and it turns out that in what we call inferential statistics, which is what we're learning about now, in inferential statistics where you infer things about a population, we've always got these two numbers. One is, we've got many numbers, but two of the key numbers are the true value of what that number is, like say the true, I've got here the real average age of Macquarie students, which would be if you could get all 40,000 people to do the survey and they all answered truthfully, etc., etc., there is this population parameter, well, that's what we call it, a population parameter of which there are many population parameters, but one of them is the average age of Macquarie University students. And we could do the same thing with the average household income of Macquarie students. You can think of that as another population parameter. You can think of the average age of an Australian, etc. Now, it doesn't have to be an average. It could be many other things, but let's not get confused about that yet. The thing is that there is, in a sense, in statistics, there's the idea that there is this real thing that you can never actually see directly, at least with the amount of finances that you have, but which you can infer. It's kind of like something, it's a thing behind a screen that you can only measure indirectly. And what you use to measure it indirectly is your sample, right? So you've surveyed 1,000 people, and what you do is with your sample is you basically do the same calculation, right? You calculate the average age of your sample, or the average income of your sample. And from that, you use that as basically a best guess, what's called the best point estimate, but just it's the sample statistic. It's the best guess at what the population parameter is. That can be, and that's the first approximation, just what we're trying to do with the sample, right? We want to know how many women there are in the population. Well, we randomly survey 1,000 and then we find out the proportion is 51% or 52 or 49 or whatever it is. So those are your two key numbers. The population parameter is the number behind the screen. The sample statistic is the number in front of the screen that's based on less data, but is generally a good approximation of the population parameter. If you've got a good sampling technique and a good survey design, and you've got a good random sample. But there is another problem, which is that you get that point estimate, that sample statistic, but it's clearly not necessarily exactly accurate. I mean, it's rarely going to be perfectly accurate, right? Say the sample behind, the population parameter behind the scene is based on 25 million Australians. Yours is based on 1,000 Australians, right? Or 40,000 Macquarie students and 1,000 people you surveyed. So what happens both actually, what happens within any, I'm clumping a few things together here. But what basically happens with any trait like age, or any trait like the average age or such, is that or you have a sample, but say any trait like age or income, is there is variation within the population. And that's why I've given this first title here, the concept of variability. So within a population itself, so say within the Australian population, there is variance in age, or variation in age, variability in age. And often another number we want to get to, another number we want to obtain is a number to express what that variability is. In the case of within that population, the variability we can call it is called the standard deviation. There is also, however, another variability that's really crucial for inferential, and this is basically not inferential statistics. This is whatever you call the other type of statistics. It begins with the D. Descriptive statistics. However, with inferential statistics, there's another type of variability that we're really interested in, which is the variation of the sample statistic which we calculate. So, and we know that, behind the screen is the true parameter, and also behind the screen is all the people in Australia, right? Let's say their average age is 40, and 95% of them are between 20 and 80, or such, or between, no, not 20 and 80. Yeah, they're over 18, so between 20 and 80, the average age is, say, 50, right, of voting people. Behind that screen is all the people and their true average age, right? But in front of the screen, we have a sample. And that says that the age according to the sample is, say, 53, for example. But we want to know if we want to know how accurate that is, what we do is we think about that sample statistic as really just one potential sample statistic we could have got if we repeated that survey. So even though we're not going to repeat that survey because it would cost us tens of thousands of dollars, we can imagine that what we see, again, in front of the screen is really just an example of all the potential surveys we could do, and of the or sample means we could calculate, sample statistics we could calculate, based on many different samples we could do. So again, if we just repeated the same study, we had another $10,000 or $20,000 lying around, we could survey another 1,000 people, and we might find out that the mean, the sample statistic for the mean age that we find is actually 48. That's interesting. And then if we had another $20,000 lying around, we might do another time, and we might find that the average is 51 or 49 or 50. And if we had just lots of money sitting around, we could repeat it, right? And we would get basically a different sample means for each different sample. Now note, okay, so the key thing is to say that the variation of that sample means is what we're interested in inferential for statistics. Because it turns out that the variation in that sample means gets smaller and smaller. It gets more and more accurate as you have more people you're surveying, which is sort of obvious, right? Like small sample size, I surveyed 5 people. Well, what can you conclude from that? Not much. 100? Oh, a bit more. 1,000? That's pretty good. 2,000? Okay, cool. I believe you, right? So it turns out that when this second type of variability, variation of the sample mean, from the population mean, acts very differently to the variation within the population. And it actually tends to be very narrow once you get large sample sizes. And we use a slightly different measure, which is called standard error. These look very similar, and they kind of, at some level, are very similar. They express how much a number varies within a set of numbers, but the standard deviation expresses how much a number varies within a population. So say age varies within the population, or the standard deviation within your sample would be how much age varies within those 1,000 people you sample. Whereas standard error captures how much that sample would deviate from the estimate of the mean if you repeated it. That. Okay, now I know you're not going to understand all that, and this isn't a statistics class, but if you can just try to get on top of this, it will make much more sense as we go through the class. And this then relates, right, to the last point, which is actually the variability and the standard error, standard deviations. For us as social scientists, they're mostly just ways to get to this last point. Because when we do science and social science, and we're doing quantitative social science particularly, we want to not just know what we think, right? What we think the truth is. We want to know how confident we are that that is the truth. And so, you could say how likely, you could say, who do you think is going to win the election, state election in a week or two? Maybe Labour. And it's like, how confident are you of that? Because they're a little bit ahead in the polls. How confident are you of that? Not very confident. I reckon maybe there's a 60% chance Labour will win and a 40% chance the Liberals will win. Will form government. Okay, but if there was a really big margin, then maybe you'd express it somewhat differently. And so the way we tend to express that sort of confidence in social science or quantitative social science is talking about a confidence interval. And that confidence interval is basically the range within which 95% of cases, whatever it is, will lie. Now, in the case of a population, it means the 95% of the population are within. It turns out there's this key number, 2 standard deviations either side of the mean. So that means a 4 standard deviation width. Which again sounds like big words, it doesn't really make sense. But if I can give you a simple sample, so if we have an Australian population with a mean, Australian voting age population, so over 18, with a mean age of 50, and there is a standard deviation, which is the number you calculate, we leave that to statisticians, but that is calculated a standard deviation of 15, then that tells us that all people, or 95% of Australians, will be within 2 standard deviations above, so 30 plus 30 years above, so 50 plus 30 is 80, or 30 years below, 50 plus minus 30 is 20. So all 95% of Australians, if they are distributed normally, which in general things are, and which is, there's various assumptions, 95% of Australians over the age of 18 will be between the ages of 18 and 80. Okay, that's pretty cool, and that tells you something, right? And that gives you a kind of like a 95% range for the confidence interval for where you would think a person who you randomly drew would come, their age would be between. For a sample statistic, so we were talking about for a population, now we're talking for a sample statistic. It's basically the same maths, but instead of saying 2 standard deviations above or below, you say 2 standard errors above or below. But remember that the standard error is actually generally much smaller if you have a big sample size. So if you had a sample of 1,000 Australians and you found that their average, 1,000 Australians and you found their average age was 50, you probably, and this is very roughly, but you probably would have a standard error of about 1.5. And that means that you're sure that the average sample, the average sample size is, sorry, the average sample statistic for the average age is between about 53 and 47, right, which is 2 standard errors above and below. Why does that happen? Well, that happens because once you're serving 1,000 people, and you're doing it properly and randomly and with good design, that the randomness takes out most of the variation itself. And therefore, the 1,000 is a pretty good approximation for the overall population. That's the point of sampling. So while there is some variation in how accurate a sample statistic is, it often, in many cases with a big sample size, is quite a lot narrower. Anyway, that's just a quick introduction. We're going to deal with these concepts more and more as we go on later in semester, and if you do statistics, you'll deal with them more. Okay, so that's the end of our foundational concepts. This last part, I'm just going to deal with 3 basic issues. Four basic types of random sampling. So these are the types of sampling you need to do if you're going to use statistics, right? Or ideally you should use if you're going to use statistics. Let's go through them. So what's called random here, but actually I guess the proper word for it is simple random sampling. It's simply when you have a population, say the 25 million Australians, and you have the electoral roll, and you simply randomly draw from within that. That would be an example of truly random sampling. It's fine, it works, we already described it, I don't need to go into detail. The next type that you could use, which is really an approximation of random sampling, is systematic sampling. So you might say that the electoral roll has got, I'm making it up, say it's got 1,000 pages. You pick the last person on each page of those 1,000 pages. And since they're organized alphabetically, it's pretty much an approximate random sample. I've put here as another example, you choose every 5th, 10th fridge to test. So often systematic sampling is used as examples from production lines. I don't quite know why. But yeah, if you're on a production line and you're in charge of quality control, every 5th, 10th fridge you produced might get a really thorough checking. And that would be an example of systematic sampling. Of course, the problem with this is that there could be some bias. It could be that back in the production line, there is actually errors that are happening to the 9th fridge, the 19th fridge, the 29th fridge, because some widget that's making things, or some part of the factory that's making things, makes an error every 10th time, but on the 9th object. And that would never get picked up by your random sample or your systematic sampling. So there's always a potential bias there with systematic sampling. More powerful than random, there is actually a method more powerful than random sampling, which is, I think the way to imagine this is quota sampling with, I mean, it's not quite that, but it's kind of doing a version of quota sampling with random sampling. What you do is, if you say you got that list from Macquarie Uni of 40,000 students, maybe you could divide it into men and women, and then you actually draw the sample. You draw, say, you know that within the population of Macquarie Uni, 53%, 53% or 56% probably are women, and 46 are men. You would then randomly draw from the women to get to 54% of your sample, and men to get to 46% of your sample. Or often this is used more when there is a very small population, but a significant one, and one you want to make sure you get representation of. So say there are, amongst the 40,000 students at Macquarie, how many would there be? There would probably be maybe, say there was 800 Indigenous students, but I don't know how many there are. Then you would make sure that you draw a sample. What are we doing? We're doing 1 in 40 Indigenous students was represented to make sure that they were actually properly sampled in your survey. This is stratified, and like quota sampling, turns out to be incredibly powerful at improving the predictions of and the accuracy of any survey, simply because it takes account of a whole lot of latent groups that we already know are there and weights them correctly. The last type of random sampling we're going to do is called cluster sampling. Now, cluster sampling is a type of sampling which you use when you want to do random sampling, but you don't have a sample frame. So the example I always like to use is early childhood educators, colloquially known as like preschool teachers, or childcare teachers, childcare center workers, but early childhood educators is their preferred name. And say you want to do a survey of all early childhood educators in Australia. Well, there's probably not a list of all those workers. I don't think there is, right? What you could do instead, and this is generally what's done, is that you do a sort of multi-stage random sampling where you say you can't get a list of all the people, but you can get a list of, say, all the companies, right? And so you get that big list of all the companies, and you do a random draw of all those companies. And then from within that, you do a random draw of one of their centers, which again you could probably get from those companies. And then you go to those centers and you, say, interview the second oldest person in at the center, which would be sort of some sort of random person within the center. And through doing these 3 steps, you can get a very approximate random sample of early childhood workers. This is used in some different types of surveys where they may have postcodes, and so they randomly draw postcodes, then randomly draw people within those postcodes, or randomly draw postcodes and randomly draw streets within those postcodes, and randomly find a house, and then go into the houses in those streets and say, I want to interview one X person in the household. And through those sort of approximate methods of clustering and semi-random selection at each of the layers, you can actually get a pretty random sample of ultimately the sampling elements or units of analysis you're interested in. Okay, so that's that. Very quick review. So we have all these types of non-random sampling, which attempt to solve problems like some of them just for convenience, so that which you don't mistake for random sampling. But convenience, where you just do it and get it done, and it's ugly and it probably doesn't mean anything. It's okay. Quota, where you match your haphazard data to census categories, and that makes it quite a lot more accurate. Purposive, which is often used for qualitative data, or where you just try and make sure you have representations of various groups you know might be underrepresented in your data. And snowball sampling, which is used for hidden populations who are basically trying to hide from society because of social stigma. And then, to review again very quickly, In terms of the foundational concepts, we need to remember there is two different types of surveys we can do. We can do a census, which is the whole population, and samples, which is a small part of the population to represent the overall population. We also can distinguish between the universe and the population in any study. So the universe is who we're drawing conclusions about, who we're generalizing to, which might be all of humanity, or it could be all students in Australia or such. And the population, just that single word means in a very general terms who is being studied, who we are trying to study. That again differentiates from the population of the target population, which is that population expressed in very specific terms, such as all Macquarie students in April 2019, which is then distinguished from the sampling frame, which is the actual list given to you by the administration of each of the people. And that sampling frame is made up of people, which we call sampling elements. And note that while I've been applying these to cases where it's about people, you could apply, the point of this language is it could be applied to, rather than the sampling elements being people, they could be countries, or they could be postcodes, or they could be a whole lot of samples of rocks in geology, or a whole lot of samples of different species in biology, and so forth. The point is this language actually, the elements don't need to be people or participants, but in social science they generally are, except when we're studying states. We then talked about two types of fundamental concepts, the population parameter and the sample statistic. The population parameter is the true value that we can't see, but it is a number that we can calculate, such as the real average age of students at Macquarie. And then we have the sample statistic, which is what we actually get from our sample. And that is the average age of the, say, 1,000 people we sampled, average age of our sample. And it's what we use to infer about what the true population parameter is when we do sample statistics or inferential statistics. The last bit here, sorry, I've just skipped forward a little bit, is that, I lost it again. But anyway, yeah, the last 2 points here are the notion of variability and confidence interval. With variability and confidence interval, it turns out that sample statistic and even the people within the population vary, right? So there are two types of variability. We talk about the variation within a population or within a sample, and then the variation of a sample as you take multiple samples. When we have a population or a sample, we can calculate the standard deviation of that. We talk about the variation across different samples. So if we had lots of money and repeated the study, then that's called the standard error. And from these, we can then calculate things like confidence intervals, which is, while say a sample statistic or a population parameter gives us a point estimate, the confidence interval will tell us a range within which either in a population or a sample the people lie, or with a sample statistic or a sample estimate, it will tell us the range within which we are confident that that sample statistic would be if we kept repeating the experiment many times. And we tend to use arbitrarily this 95% confidence interval. Okay, and then lastly, we have 4 types of random sampling. We have true, simple random sampling, where we literally just roll a die, generate a random number, pull it out of a container, and it is just truly random from our sample frame. We have systematic, where we just pick, say, every 10th or every 20th or every 300th person, but it has the potential that there could be some underlying bias we miss. We have stratified samples, where it's basically true random sampling, but we sample within pre-existing groups that we know about, so that we get the exact proportions of those represented in the final sample. And then we have cluster sampling, where we don't have the people we want to survey, a list of them as a sampling frame, but we do have larger entities which we can randomly sample between, and then moving down through this hierarchy, eventually get a relatively random sample from the state to the postcode to the locality to the street to the house and to the person within the house. We randomly sample at each of those different levels, and eventually we get a pretty good approximation of a truly random sample. Okay, so that's the end of this first part of the lecture. I will finish there. Thank you very much, and don't forget to go on to the other 2 parts of this lecture for this week.